All right. Hi, everybody. Whoever it was that stopped by my office to say hi, but we never actually got to say hi, sorry. But if you come back next time, I'll be there to say hello better. Sorry, we were wrapped up in a math problem. Okay, anyway, so today we're going to be talking about compression. Today in Wednesday's lectures are application lectures of things we've done before, a little taste of other things we might do in the future, and then Friday we'll wrap up and do some general summarizing. So first, let's talk about compression. I remember when I was at the tender age you guys are, I was somewhat mystified by the idea of zip files. The idea that I could take a file and I could zip it up and then somehow it's smaller. And what's more, after zipping up, say, the text of Moby Dick, look, it's smaller, 261,000 bytes, there was also the unzip command, which I could unzip Moby Dick and I get back the original file. What is this magic by which a file can be made smaller? In this case, much smaller. And this line here is just noting if I compute the difference between Moby Dick and the unzipped version, then they are not different. That's what this diff command, by the way, does. So how does that work? Well, that's what we're going to be demystifying to some degree today. There's actually a number of algorithms for doing this. We're going to do one called Huffman coding, which maybe you've heard of, maybe you haven't. So before we could do this, then, we need some kind of model for what our process is going to be, and that's as follows. We're going to say that all of the data that we have out there is just bits. We've alluded to this in the past. You have some sense that anything could be represented by zeros and ones. And in 61C, you'll come to understand that on a deep level. But, suffice it to say, given a bunch of data, I can represent it, whatever it is, as zeros and ones. And so what we're going to do is talk about compression algorithms, in this case one called C, that takes a bit stream B and gives me back a compressed set of bits. And we would like there to exist an inverse algorithm, right? So we can actually get back what we had in the first place, and we will get the original file back. Okay. Now, what we're going to assume for now, and we'll relax this assumption and change things up a little bit later. But what we're going to assume for now is that in a lossless algorithm, no information can be lost, and that means that by that I mean you get the exact bit stream back. There's no error here. And in the extra slides, we explore what happens whenever you have lossy compression. Now, what we'll find is interesting, and this will end up being a very deep fact mathematically. It's interesting that text files, as you and I store them on our computers, that they're often compressible by 70% or more, which is a pretty impressive feat. In the case of Moby Dick, right, we got about, almost a third. Okay. All right. So how does that work? Well, I'm going to start by talking about something known as a prefix-free code to get a sense of where there's waste. So the only reason we're able to compress text is because it's currently stored wastefully. And so by default, what I'll note is that English text is usually represented by sequences of characters, and in the case of ASCII, they're each 8 bits long. Now in Java, technically speaking, characters are a little bigger, but the original idea of characters was 8 bits each. And so for example, D, because some consortium at some point, ASCII, got together, they decided that D is going to be 0, 1, 1, 0, 0, 1, 0, 0. And you can think of these last 4 bits, the letter D, it's the 4th letter of the alphabet, so that's why that's 100 there. All right. Just a historical fact. So if we think about the word dog, it's this sequence of 8 digits for D, this sequence of 8 digits for O, and this sequence of 8 digits for G, and in hexadecimal, which we discussed, I think, very briefly at some point in an earlier lecture. This is just an alternate way of writing out this binary number, but not particularly important. Okay. So and this is not going to be satisfying to you guys necessarily, but the easy way to compress is going to say, well, obviously, how many letters are there in English? There's only 26, so it seems a little weird to use 8 bits to store your 26 combinations, or even if you include capital letters, that's still 52. That's way fewer letters than we get out of 8. Okay? And so that's what we're going to rely on. And what we'll see is this technique generalizes beyond just alphabetical characters. But what we'll do here is say, we're going to use fewer than 8 bits for each letter. And that means then we're going to have to decide, instead of using ASCII's rules, that D is this 8 letters, we're going to pick some shorter sequences. So we're going to decide which bit sequences go with which letters. Instead of 011001100 going with D, we're going to pick our own. And so in other words, what we're going to say is which code words, which encodings right here, this is a code word, go with which symbols. So a symbol is G, a code word is the sequence of bits. Okay, that's what we're going to try and do. Now, you guys have heard of these kind of binary mappings, these types of code words. Morse code is a very famous and very old technique for transmitting text information over wires, way back in the day. So let's take, for example, dash, dash, dot, dash, dash, dot. Well, this is this table that will tell you, given a sequence of signals being sent over a wire and Morse code, what it corresponds to. So what I'd like you to do, look at this table and figure out what dash dash dot corresponds to, just to get a sense of what this is all about. So I'll give you guys 40 seconds to try. All right, hopefully you found at least one. There are actually many answers. Two of them are meme and GG, which, by the way, was an accident the first time I did this, and I found it amusing enough to keep forever. So anyway. Now, if you're thinking, what does that have to do with binary symbols? Well, the dash and the dot weren't really important. We can think of a dot as 0 and a dash as 1, or the other way around. Now, how do you know if you're a Morse code operator if someone said meme or GG? Well, in practice, what someone would do is leave a pause. So if I wanted to say GG, for example, I would go beep, 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 beep. And that pause lets you know where the edge of the symbol was, right? And so in effect, we used the pause as a third symbol. It was actually a trinary system where there was a special end of symbol character. But there's an alternate strategy. Instead of having pauses, instead of having a third symbol, or third type of digit, I guess the word symbol here is kind of confusing. But instead of having a third alternative to 0 and 1, we can use something called a prefix-free code. So we'll avoid ambiguity. Okay, so to get a sense of this, let me show you why Morse code is problematic. So this is just from Wikipedia, from the Wikimedia Foundation. We can see here, for example, that the letter G is a suffix of M, or better put, M is a prefix of G. So if I want to go to M, it's dash dash, so beep beep. And if I get to G, it's dash dash dot, beep beep beep, right? So this here, the fact that some characters are prefixes of others, that is the problem. It means there's ambiguity. And so if we only stored characters in the leaves, then we'd be in good shape. And in fact, you could think of normal binary as that, right? We have 8 sequences of digits, and we only use the leaves. And like the letter A is over here, then B, then C, then D, and none of the upper nodes are used. Also, quick question. Do we have any visitors today? All right. No? Okay. Well, sad. Thought you might be around. All right. So prefix-free codes. Okay. So let's see an example of a code which is prefix-free, where no character is a prefix of another. Well, the most obvious one, that's very silly, is one where we just prepend a bunch of zeros, and that indicates which character number. So if we go from the start, so start is a box indicating that we're going to begin tapping out a signal. When we get if we have a 1, that means it's a space, like we're trying to indicate a space between words. If we have 0, 1, that's the letter E. We have 0, 0, 1, that's the letter T. 0, 0, 0, 1, that's the letter A. And so if I wanted to encode the phrase I ate, I would look up in this table where I is, and I would say, okay, that's 0, 0, 0, 0, 0, 1, and there's I. If I want a space, that's just a 1. That's what it says. If I want the letter A, that's 0, 0, 0, 1. And what's nice about this approach is that you don't need that pausing. There's no ambiguity. And if I see this sequence, I know that it corresponds to exactly I ate and nothing else. So this approach is better than Morse code in terms of ambiguity. It's also, however, much more inefficient, right? Like, if you look at this, obviously a sentence is going to take forever if it starts having like Z's in it or some uncommon characters. Now, I actually think it's worth coming back here and saying, what do we notice about Morse code? What kind of characters appear early on in the tree? E and T, what's special about those? They're common, right? And the uncommon ones go at the bottom. So that's the table here. So here, we've done the same trick. We've said, okay, well, we want prefix-free, so we're going to make E and T and A very common. But here, because we're enforcing that the characters that they get 1 longer for every level of rarity, so to speak, it means that the letter I is very expensive. So there are other approaches to getting prefix freeness than this. So for example, we can actually have a less stringy tree or less spindly one. We can get a bushy tree that's still prefix free. So here's a code I just made up where, for example, space is 111. That's space. T is 1101. A is 1011, and so forth. And so in this case, if I write out I ate, well now I is 1000, 1000 I. Space is 111, and so forth. So the space character costs more, but I costs less, And the average amount here, we can get a relatively more compact representation, perhaps. All right, any questions about what we've done so far? All right, yes. This one might be more space than the previous one. You're saying this one might be inefficient? Mm-hmm. Yeah. Oh, the space button is more than the letter I? That's because it's only 3. So that's 1, 1, 1. So it takes 3 bits for the space and 4 for the letter I. Oh, so we have 1, 1, 1 for space. We know we're done with that character. Okay, so then how do we differentiate that from what else? Yeah, so the point here is that you don't have to worry about differentiating. As soon as you see the boundary of a character, because you've hit a leaf, you know you can go back to start. It's safe. Okay, so as soon as you hit a leaf, that means go back up. All right. So how do you get a code? Where do these prefix-free codes come from? Well, I'll first start by saying here's 2 of them. This one seemed really inefficient, the one that was a long, spindly tree. This one maybe seemed a little better. It's bushy, but it's actually not really, strictly speaking, true. If I had a string of, say, E-E-E-E-A-T, eat, for example, that's 15 bits with this code, whereas it's 20 bits with our other seemingly bushier code. But my name, for example, Josh, in this code is going to be 48 bits, but over here it's 23. So depending on what you're actually encoding, it may be that some prefix-free code's better than another. So the observation here is that, well, it'd be nice if I had a procedure that, given a text, like the Declaration of Independence or whatever, I find the best code for that text. That might be a useful thing to have, for example. I think it might be cool. So this is actually a really old story. All right. So my native Chinese speakers find this funny. It's a good story. You can Google it later. Anyway, not worth explaining. All right. So I picked these 5 arbitrary Chinese characters, and let's say that I have a text where 35% of the characters are this one, which I didn't bother to look up this time, but it doesn't matter. You can just look at it and be like, okay, that one. Okay. I don't want to alienate my English-speaking audience. I'll avoid speaking Chinese. Also, I don't speak Chinese. All right. So what we're going to do then is imagine that we have a text file that's just these characters. For some reason, I'm just writing some absurdist poem about Li Gong. Okay. So what I do is I have, let's say 35% of the characters are this one, 17 are this, 17 are this, 16 are here, and 15% are those. Okay. Now the Shannon-Fano coding procedure says, given these frequencies, and notice they sum to 1, because I'm just counting the relative amount, so 35% are that character, I'm going to split my space of possible symbols into 2 halves. This is just something that Shannon and Fano came up with. I haven't proven it to you or anything, but I think it'll make sense in a moment. And so what we'll do is the left half is going to get a leading 0, and the right half is going to get a leading 1. Okay, so what I mean by that is, I have now decided that all of these characters shall start with the digit 0, and these shall start with 1. Okay? Now that I've done so, I need to differentiate these 2 characters. So one of them is going to be 0, 0, and the other one's going to be 0, 1, and so we're just going to recursively repeat that procedure. Okay? Now the goal of the split, now this is an important point I don't think I made very clear, is that we made the split at this point because roughly half of the weight of the characters was on the left-hand side, right? You look at 35 and 17, okay, well that's 5, 2, 52%, okay? So that's about half were these characters put together, okay? So now I've decided the left half is going to get a leading 0, the right half gets a leading 1, and we repeat. All right, so I'm going to do this recursively, and now that means that this character is going to be 0, 0, this one's 0, 1. Okay, over here, if I wanted to split these up, which one should I... So ultimately what's going to end up happening is I'm going to split it so that one of these characters is a 2-digit character, like it'll be 1 something, and the other 2 will ultimately be 3-digit characters. I'm going to split this in half. So which one do you think should be the shorter symbol of these 3? First one. Good. All right. So I'll say this is the left half and this is the right half. Okay. All right. So now I only have 2 symbols left, so I'll split those in half, and I end up with this code. This is Shannon-Fano coding. Now, I'm not going to belabor it too much because we'll see that this is an obsolete code. But this was the best known way to generate a table of code words for a particular set of symbols for a long time. Okay? So what I'd like you to do now, let's try and digest that. And the question, and I actually didn't shout key it, sorry, I was just too wrapped up in office hours to do it. I had time to do it too. Oops. Oh well. Anyway. So question, how many bits per symbol do we need to compress a file with the character frequencies listed here using the code that we created? So in other words, what I want you to do is figure out if I had, say, 1,000 symbols, 1,000 of these characters, and it had obeyed these frequencies, how many bits per symbol would I use? And what I like, and this is just some time for you to try and digest this, okay? So this is the code we came up with. This is the relative frequency, and good luck. All right. If you're not sure where to start, you can think about unit analysis from chemistry class. All right. Okay. All right. How many bits per symbol does it take to do these three characters? This symbol, for example, takes how many characters in our table, or our code word set? 2. This one takes 2. This one takes 2. This takes 3. This takes 3. So, in other words, every time we use one of these characters, we're doing 2 bits per symbol. And that happens 0.35 plus 0.17 plus 0.17% of the time. And the other 31% of the time, it takes 3 bits per symbol. So in all, it takes 50... all right. Well, I think this example is even easier to see. All right. So you can think about it that way of how many bits per symbol happens, what fraction of the time, or personally I found it a little easier to think about it this way. So let's assume we had 100 symbols. Well, if our frequency is that 35% of them were this top character, right, because that's just what it says right here, 35% of them, then it's 35 times 2, which is 70 bits. So we'll spend 70 total bits encoding our 35 of these. We'll spend 34 bits encoding our 17 of each of these, 48 bits encoding our 16 of these, and 45 bits encoding our 15 of these. Why 45? Because it's 15 times 3. So in total, that's 231 bits. And how many total symbols do we have? Well, it's just the sum of these, which is 100. So it's 2.31 bits per symbol. All right, any questions about that? Okay, so with this setup, it takes 2.31 bits per symbol. That's the cost. Now, if we were using just plain old Unicode in Java, say 16-bit Unicode, well, each Unicode character is 16 bits per symbol, which would be more expensive. Okay, so I'd like you to actually put a number to that face and see if that all made sense. Okay, this is your second time to try and digest this and make sure it really makes sense. If we had a file which has 350 of these, 170 of these, 170 of these, 160, 150, how many total bits will we need using 32-bit Unicode, which is the real-world standard? And how about using our code? You don't need a calculator. I'll give you a hint. There's 1,000 total characters. Okay. All right. So if you're using 32-bit Unicode, if each symbol costs 32 bits, how much do you need for 1,000 characters? 32,000. All right. If you're using our code, which only uses 2.31 bits, then it's 2,310 bits. That's 14 times as efficient. That's pretty good. Now, the downside here is that we can only encode strings that have these symbols. And let's say somebody only uses this symbol over and over, then it'll be better than using Unicode, but it won't be as efficient. Now, as long as the distribution of characters exactly matches this frequency, then it'll be only 2.31 bits. Okay. All right. Now, it turns out that Shannon-Fano coding is not optimal. It does a pretty good job. 2.31, obviously much better than 32. But It turns out there's a better approach. Now, there's actually an interesting story behind this. I won't tell the whole thing, but basically, Huffman was in a graduate class, this guy who invented the thing we'll talk about in the next slide, and I think it was either Shannon or Fano teaching it, and they basically said, well, we've observed that our code's pretty good, but we've made up some codes that are better, so how do you find the best code, right? We don't know how to mechanically generate the optimal code, so if you do this, you will get an A in the class. It was a grad class, and you want to take the final. And so Huffman, he decided, okay, I'm going to try and do it. Let's try and figure it out. And he apparently, supposedly the story goes, he just tried and tried and tried, and eventually as he was throwing his notes in the garbage to say, okay, I'm going to go start studying for the final, he realized at that moment. Now, that seems a little dramatic to me, so I think he's not telling the truth, but oh well. Anyway, so if you go here, you can read about, I guess Huffman's nephew made a website called HuffmanCoding.com, where you can read about his uncle. And I don't know what else is on the website. Maybe it's about Huffman coding itself. But how does it work? Okay. So Huffman coding, it's interesting because it's it feels like, well, yeah, this would be the first thing you tried if you didn't do it this way. It's like the perfect duel to Shannon and Fano's approach. So instead of going top down, all Huffman does is go bottom up. And so what he does is he says, let's start with our 5 characters and attach their frequencies at the bottom. Then we're going to take the 2 smallest and merge them into what I'll call a supernode. So each of these is a node for now, but we'll merge them. So once I merge 0.16 and 0.15, I now have a supernode with weight 0.31. Okay, so now I have 4 nodes. What are the 2 that have smallest weight? Give me their weights. 0.17 and 0.17. So let's merge those next. Now we have 3. What are the 2 smallest? 0.34 and 0.31. Okay, so those get merged, and that's 0.65. Then we finally merge everything into one big tree. We have produced now the optimal code. That's it. Okay, so I've just done Huffman's homework that took, 2 months and a lot of struggle. Now, what we've not done is proven, crucially, that this is optimal. That was part of his homework. But it turns out that this is the optimal approach, and if this is something that you think is really exciting, there are courses where you can learn about things like information theory, which is really fun. I think that's in 126, towards the beginning. Okay, so it turns out that the Shannon-Fano code before we computed together took 2.31 bits per symbol. It turns out with this Huffman code, we could do the same exercise again, but I'll spare you, would be 2.3 bits per symbol. It's the same exact problem you did before, but now it's 13333 instead of 22233. Okay? Now what's interesting about this approach is that this 2.3 bits per symbol is just strictly better. This code, the Huffman code, is just better in every possible way than the Shannon-Fano code, so there's no reason not to do this. Okay? There's no downside. That's rare. Isn't that nice? All right, good. All right. So now I got a data structures question for you. Now that we have a way to find the optimal code, let's suppose that we have a bunch of symbols, in this case characters, like I8. How do I go from those characters to a bit sequence? And let's just assume that I have a type called a bit sequence that stores, say, 00001, and don't trouble yourself too much with what those are exactly. So I'll give you guys only 30 seconds. Try and think, what data structure do you need to turn I8 into this sequence of bit sequences? Okay, how do you get from I to this bit sequence? What might you use? Yeah. All right, I like both of those answers. So you could do an array of bit sequences or a map of bit sequences. In this case, a map from character to bit sequence. Now, I would say that depending, I like that answer, that depending on how dense, like how many characters you actually end up using, an array or a map might be better. Now, what I'll note is that a map will be a little slower, but it might be a little more space efficient if not many characters are used. The key lesson here is that anytime you're trying to map from a number, which a character basically is a number, to something else, an array is basically the same thing. So a map from character to bit sequence does the exact same job as an array of bit sequences. I think typically you would use an array because most of your characters are going to get used. But as I note, if some characters are not used, then maybe a map is better. I'm going to just cut it off there, but it's something to ponder. But it's a repeat of things we've done before. How about the other way? Let's suppose I want to decode. So I'm given a long sequence of bits, The bit sequence is 00001, 1, 00001, 00101. And I want to take this and repeatedly find the correct character and then move on to the next. What data structure should we use? You get 30 seconds. Okay. What do you think? Anybody have some ideas? It's kind of a tricky one. It's cute. Yeah. Yeah, try. And why would a try be good? I don't know. I see. So check the first element, the second element, the third element, and so forth. So that operation you're looking for is basically longest matching prefix, which happens to be one of the two things that tries are really good. No, in this case, the try has an alphabet with what alphabet size? What's R? 2. So it's a binary try, all right? And that try, basically, and I'll show you a picture of it soon, will have a rapid longest matching prefix operation. Now, we're little heads in the clouds here, and we'll go down to earth in a moment. So let's talk about in practice, okay? Now, the first thing I want to do is talk philosophically, and we'll come back. If this didn't totally make sense to you, what I meant, we'll see a demo in a sec, okay? But I want to think more just philosophically. Now, there's two different ways that one can imagine implementing Huffman compression. The first is for every input type, okay? So I have English text, Chinese text, images, Java source code, whatever. I collect all English texts, and I assemble some magical, gigantic, we'll call that thing a corpus. So I take the English corpus, and I build the English code word table, which is what we did with Morse code, right? Morse code's based on English. Now, for every possible, the alternate approach is, instead of taking English and building the one true English code word table, we could say, for every single file, we'll build a unique code just for that file, and because someone else doesn't know already what the code word table is, I'm going to have to send the code that along with the compressed file. So I have to tell them, here is the way to decode it, and here is the compressed file. So what I'd like you to do is think just for a minute or so, what are some advantages or disadvantages of each idea and which is better? And so the approach is that with approach 1, if you wanted to actually encode something, you would say which magical corpus to use, which code word table. And the other is, well, you actually build the code word table for each specific input. So if that didn't make sense, you can talk to your neighbor and figure out what I'm even talking about. But think about that for like a minute or so. All right. So, what do you guys think? What are some things you like about, I don't know, anybody? Throw out an advantage or disadvantage, yeah. So there are weird books like Gatsby, which has no letter E, right? I don't, is that what it's called? Anybody know this book? Yeah, all right, cool, yeah. So that one you would have a custom code word. Okay, great. I like that it's tailor-made and more efficient. Okay, yeah?
Number 2 also has like added advantage of being like, an inscription.
It's what?
The added advantage of being like an inscriptional code.
Inscriptional code?
Yeah.
Oh, encryption. Oh, okay. That has the advantage that it feels kind of encrypted-y. Okay? All right, yeah. Would have additional overhead, I guess, to build the code word table. Okay? But you have to, it's always going to be linear at least just to do the encoding and decoding, yeah. Mm-hmm. Got it. So number 2 has the disadvantage that the code itself takes up space, which is what we care about. And so there's an uncertainty here what matters more. Do you get more of a benefit by having a custom code word table versus the transmitting it along? One more thought? Yeah. A bunch of files and what? Mm-hmm. I see. So number 1, you can have one translator, but number 2 takes many translators. The code makes it so you really, or sending the code, I'm going to make a quick note here. Sending the code means that so you really just need one decoder though, so not a big deal. All right, biff deal, almost. All right, good. We went off the slide, but that's okay. All right, and those are good answers. Now what I'll tell you is that in practice, Philosophy 2 is used in the real world because in general, it turns out that the extra overhead for your code word is, your table is not very big because the input could be potentially gigantic, maybe megabytes, and the code word tables are going to be usually small. So here's a rough picture of what encoding looks like with Philosophy 2. But Philosophy 1 is valid. It just turns out to be, in general, not quite as good because sequences tend to be very long, is the short answer. Okay, so this is what Huffman encoding might look like, which is I have a long sequence of characters. This is just nonsense, but I'm going to encode it anyway. So first I'm going to count up the frequencies, and so I count them, and in this case, voila, turns out to be those exact frequencies from Favor. Great, convenient. All right, then I'll calculate the relative frequency of each character. We then build the encoding array and the decoding trie. Those are our data structures questions. So we have an encoding array and a decoding trie. I won't show the array because it's boring. Building the decoding trie is pretty simple. We do that procedure we described. Now the question is, how do we take this thing and send it, right? I mean, I guess I could take a picture and I could mail it to you, but that's not very good. But it turns out that there is a way to take this and turn it into some bits that is described in the optional textbook. Oh, and by the way, here's that encoding array. The encoding array just says take the symbol and you get back the code word. Here I said the word map, but same idea. All right, so the next part is writing the decoding trie. And what I'm showing here is the actual code as it would be written if you use the procedure from the optional textbook. It's not that deep. It basically involves doing a traversal of this tree in a funny way. But I think it's just not deep enough to be done in lecture. But if you're curious, it's an optional textbook. So after I write out this decoding trie, there exists some way to write this thing out to a file. And then the last step is to go through and for each character, write it out to the output bit. So in this case, this first character, we look it up and we see that it's 0. The next character is 0 again. All right, this next one is what? 111. All right, great. So we put that one in. All right, next 111. 111, then 101, and that's the end of my demo. All right. So that's what encoding looks like. We calculate the decoding trie. We put it in the file using a magic procedure that the book describes, and I promise you is not that deep. And then finally, we do each code word using our encoding array. Yes? Why is it a trie, not a tree? It's also a tree. A trie is a type of tree. And why it's a trie, you'll see in a moment when we do a decoding. Yes? Yeah. Well, so when we're decoding, maybe I should bring up the decoding demo. And maybe I'll take questions after the decoding, because I think I might forestall some of your questions. Okay, someone calls you on the phone. It's the middle of the night, and they say to you, 0, and it says loading. Okay, all right. I call you at night, and you hear me say 01, 01, 01, 01, 01, 01, 001, ... 00, 1, 1, 1, 1, 1, 1. And you want to know, what did Josh Hugg just say to me on the phone? All right. Good question. Well, we've already agreed beforehand that this first part of the thing I said was a decoding trie. Okay, I read that in. Turns out it's just the opposite of the procedure I've hidden from you that's in the optional textbook. Then what we're going to do is do longest prefix match operations in our decoding trie, which I've described as follows. Use the bits to walk down the trie. But that's basically the same thing as use the longest prefix of operation. And every time I hit a leaf, at that point, I will spit out the character. Okay, so the first step is reading in this decoding trie. In Project 2, you also learned about the magic of serialization, potentially. Okay, whatever, it's that kind of idea. So I get this trie read in Java. I promise it's possible. And then after you've done that, we're going to step through this try, and we're going to say, what is the longest prefix of the rest of this babbling sound I heard from Josh Hugg in my try? Well, what's the longest prefix of this in the code word table? Well, it's 0, right? And so the next symbol must be this one, so we're going to output that. All right, so now we've found the longest prefix, so what do you think we should do? Get rid of the 0. So I'm going to throw away that 0, and if I do the longest prefix again of this sequence with the 0 covered up, okay, so it's covered up, see? All right. What's the longest prefix of the rest? Also 0 again, all right? Next up, we're going to look at these. So I have 1, 1, 1, yada, yada, yada. What's the longest prefix of this in the decoding try? Well, it's 1, 1, 1. Actually, here we go. All right, it's 1, 1, 1. So which one is it? Sorry, I forgot I had this in the slides. Busted. What's the next symbol? 1, 1, 1. All right, good. We did it. I had to make you do it. All right. Wait, what's next? Same one. All right, same one. 101. Okay, that time it's 101. So that's how decoding works. All right, questions? All right. So that's all Huffman coding's all about. Now, if you build these custom Huffman coding tries and decoding tries, you can use this for text, you can use this for images, and it will work just fine. Like this exact procedure I've just described, if you take a bitmap picture of your face, you can apply this. And in that case, each symbol might be the first 32 bits of your bitmap file, and then the next 32 bits, or whatever. Doesn't really much matter, okay? So this is the approach, right? So given each file that we want to compress into, let's say, x.huff, okay? It's not .zip, it's huff, it's something else. So what we'll do is consider each b-bit symbol. That could be 8-bit chunks, it could be Unicode characters, like Chinese characters, or whatever. And when I say 8-bit chunks, I mean you take any arbitrary file, doesn't matter what it is, and you break it into 8-bit chunks, and you call each of those a different symbol, okay? So then what you do is you count the occurrences of each of the 2 to the b possibilities. So if we're talking about 16-bit Unicode, your alphabet, your encoding map, could be as large as 2 to the b possibilities. And as I mentioned, b is just the size of each symbol in bits. Because each of those Chinese characters, or each of those English characters, is also just some bits. Then what I do is I use that Huffman algorithm to build the decoding try and the encoding map, and I store the try at the beginning of x.huff, a new file. Then I use the encoding map to write the code word of each symbol into x.huff. And then to decompress, we just do the opposite. I read in the first so many bits to get the decoding try, and this is the magic process from the textbook. And then I repeatedly use the decoding try's longest prefix of operation until we get back my original files. Now, if you really want to go down to the bit level and see how things really truly work, the optional textbook describes an implementation, including, for example, write try. So if you're wondering how we write that decoding try to the file, it's just this, like, that's it. That's the whole thing. It's kind of cute, right? But I haven't told you how it works. But that's to convince you that it's just like a traversal like you're used to, okay? All right. So that's the approach for Huffman coding. And using this, you can compress files, and I'll show you an example in a minute. All right. So the big idea in general, right, Huffman coding is but one of many families. And there's another one in the extra slides called LZW that's very famous. That's a totally different approach that does something else. But the general approach for Huffman coding is I want to represent common symbols, like the letter E, with a small number of bits. That's one idea for compression. But there's other approaches. So there's one called run length encoding, where you replace each character by itself concatenated with a number of occurrences. So for example, if I have x, 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 I will do x10 instead. Y, 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 y becomes y4, and so forth. That's an alternate approach. There's a third approach called LZW, which I alluded to a moment ago, and that's in the extra slides, that looks for common patterns, like that HEF appears lots of times. Now, the general approach, across all the compression, is exploiting redundancy in some kind of order that's inside the sequence. And what you'll find is that sequences that don't have redundancy or don't have any order, they actually get enlarged a little bit. And there's actually a lot of really deep theory that we're going to take a little tiny taste of. Okay? Any quick questions on that? Okay, you know how to compress files now. Good. All right. So let's compare some compression algorithms and get a sense of how things behave. All right. So different compression algorithms, Huffman, LZW, run length encoding, they get different compression ratios on different files. So we'd like to be able to compare them in some way to say this one's just better than that one in some circumstance. Okay. Now to do this, we have to refine our model of bit streams from the beginning of lecture. We had B and C of B to be a little bit fancy. And so let's start with a little bit of a tiny puzzle, which is let's say I just tell you, I came up with SuperZip. Okay? It's so good that you give me any bit stream, and I guarantee that you can get that bit stream shrunk to 50%. Why is that impossible? Yeah, anybody want to maybe solicit a back of the room answer? Yeah. Yeah, you super zip till you get 1 bit, and then you just super unzip. Well, it seems a little unlikely that any algorithm exists that if I give you the number 1, you can tell me which original sequence we got, all right? So if I took the sequence of bits and I compress, I get 1 bit, and then I just uncompress over and over. Wow, great. Fractals. All right, I don't know. So that one will not work. That's argument 1. Can't do that. Now, there's another approach, which is a little mathy, but I think really interesting, and this is like getting into 170 territory a little bit, or maybe 70. So it turns out, as no surprise, that there are far fewer short bit streams than long ones. So there's no algorithm that can even do this once for all bit sequences. It's a pigeonhole principle, okay? So for example, let's suppose we were talking about 1,000 bit sequences. That's not a lot of data, but there are quite a lot of different sequences that are length 1,000. So there's 2 to the 1,000 bit sequences, but they're only, well, okay, what sequences are shorter than that by a factor of 50%? Well, maybe you get lucky and you get no bits at all, or 1 bit, or 2 bits, or 500 bits. And so the total number of different bit streams that are 500 bits or fewer, you could do the math, is 2 to the 501 minus 1 bit streams. So what we're saying is if you had an algorithm that could super zip even just once, do 50% for any bit sequence, that would mean we have 2 to the 1,000 different sequences, but only 2 to the 501 minus 1 bit streams to represent them. And this number, while, it's exponential, so we don't really have a deep appreciation of it as humans, this is far smaller than 2 to the 1,000. So in other words, you have 2 to the 1,000 things and only 2 to the 501-ish places to put them. And so what we could say is just by chance, if we took an arbitrary 1,000-bit input, right? I just go and I slam that, right? And I get some number of bits. The number, that's a good idea. Okay, there we go. It turns out that of those random sequences I might type out, if I typed out zeros and ones only roughly 1 and 2 to the 499 can be compressed by 50%. So any bit stream that could be compressed by our algorithm, we got very lucky. Like, this is pretty good odds. If someone, or bad odds, I guess, right? Like, if I was in Vegas and they said, you have a 1 and 2 to the 499 chance to win, I would say, no, I will not play your game. All right. Now, there's sort of a sneaky situation here, which I want to address, which sometimes students point out. While universal compression is impossible, it seems like there's some tricks you can play, all right? For example, let's suppose we build a special purpose compression algorithm that simply takes small bit sequences and turns them back into large ones. So I want to take this episode of Game of Thrones downloaded from the Pirate Bay, and I want to distribute it as 010. Well, then all I need is a decompression algorithm that is capable of taking 010 and outputting that thing, right? I mean, that's possible. I can write this program. If you give me the input 010, I give you this, okay? Now, what does that mean about my decompression algorithm itself? It needs to be what? Relatively complex. So maybe it takes a whole lot of bits, okay? And because what you would do is you would basically write the episode itself into the decompression algorithm, and if you get 010, you say, okay, you can have the episode, okay? So that seems like cheating, and that seems like it's going to make comparing algorithms difficult. However, we can deal with that. And this is the part where we're going to make our description of our algorithms a little fancier. So we're going to include not just the bits needed to encode the compressed bits, but we're going to talk about the bits needed to encode the decompression algorithm itself. We're not going to include the compiler or any of that. We can call it a day, just including only the algorithm that does the decompression. And that will be good enough for our purposes. Okay, so once we've done that, then we can start talking about some really weird, deep stuff. Okay? So as a model for decompression, what we're going to do is we're going to treat the algorithm and the compressed bit stream as a single sequence of bits. Okay, that's just for our convenience. And if you want a concrete idea, if you're like, what does that mean? How can the bits and the algorithm both be a single sequence of bits? Well, we can imagine that the compressed sequence is a byte array variable in Java, so it's all the data that you would send, plus all the code needed to decompress that byte. And we'll see an example in a minute. And so ultimately, what we're thinking about is the algorithm and the compressed bit stream together. They're an input to an interpreter, and the interpreter somehow executes those bits, and you guys already wrote an interpreter if you took 61A. Now, if you didn't take 61A, this is still a mysterious black box, but that's okay. Now, at the very bottom, right, the interpreter has to run on hardware. and that's in 61C, but we're gonna call it a day and not worry about those details. There exists a magical black box that can interact with the hardware and take our self-extracting Game of Thrones.java and give us back an MP4. Okay. All right. So that's going to be our model for compression. And what we're going to talk about here for a moment is how well can we do. So all right, let's take a break. It seems like we've gone on to like a weird, been all over the place. What's going on here? Okay. What I want to do here is talk about the ultimate limits of compression. And what I've just said is we're going to treat the compressed bits as also including the algorithm itself. Okay? So for example, maybe this will elucidate it very carefully. So Huffman coding can be used to compress any data, as I mentioned. You just break it into 8-bit chunks and then run it through Huffman coding. So in bitmap format, if you open up this plant that I made using Java a long time ago, back in 2011, if you open this file up in a hex editor, which is just a file for looking at binary data, you would see that this plant is represented on my computer as 42, 4D, 7A, 00, 10, 00, 00, and so forth. In total, it was 8.4 million bits. That's the original uncompressed bits. If I Huffman code this thing, it turns out that using that procedure I described, the coding try, or really the decoding try, to be fair, sorry, let's fix it. Okay, you guys aren't busy, right? Okay, we got 5 minutes. Oh, no, it's too big now. All right, we might have to keep fixing it maybe, but I want to make sure that's clear. So we have a decoding try that it so happens when I ran the experiment was 2,560 bits, and the image data, the rest of the stuff, all of those encoded bits, is 1,999,000 bits. So in other words, we went from 8.4 million to around 2 million. That's pretty good. So all this stuff is in one big old file called hugplant.huff. But if I tried to actually open this thing, right, the 2 million bits, if I'm in macOS, it will tell me, you know what, hugplant.huff, that's not a thing. I don't know how to open huff files. And that's why we also need to include the actual code for the decompression algorithm, the 43,400 bits. So when I say that we're going to represent the algorithm and the compressed data together, we're going to imagine that we're going to include all of this. Okay, this is just a tiny bit of overhead, but I just wanted to be really honest. All right, any questions about this setup here? Yes. Could I send the .class file? Yeah, probably, but yeah. All right. Okay. Now, to keep these conceptually simple, because I don't want to be talking about these separately, let's package the compressed data and the decoder into a single self-extracting Java file. So it's going to be the Huffman code and all of this data. And so I have self-extracting hugplant.java, which consists of the code for this is the Java, this purple stuff. This is the decoding try, this red stuff, and black is the image data. And so in total, I have 2 million bits that if I type Java space self-extracting hugplant after compiling, I will get back hugplant. So this bit stream, in other words, you take it, you hand it to the Java interpreter, and it gives you a bigger bit stream. And this is the model of compression we're going to have. I have programs that are given to interpreters and giving back more bits. In this case, these 2 million bits give me these 8 million bits. Okay. So what we've now seen at this point, we have self-extracting hugplant.java, which is 2.1 million bits or so. It goes into interpreter, and I get hugplant.bmp. Now, this is a lot to digest. So I'm not going to go into the details of what I think is super cool about this. We'll get there in the next lecture. So let me make sure. I'm going to take a couple questions, because I think this is a really easy little set of points. So in our last, 60 seconds, any other questions you guys have for me about the setup? Yes? Yeah, so what would happen if we were to take self-extracting hugplant.java and run it through the same process we used to generate it? Would it get smaller? It turns out in this case, because of the way hugplant... so we look here, is there order in self-extracting hugplant.java? Do you notice any patterns? I see some. There's a lot of Fs. All right? That is actually order. So it turns out, and I did the experiment once, if you run this again, you get an even smaller file. So if you Huffman code this file twice, what that kind of tells you is Huffman coding is not great. It's like you take a wet rag and you squeeze it and water comes out. You can squeeze it again and more water will come out. Huffman is the same way. It's not a really advanced algorithm, but it's easy to understand. So if you encode this again, it gets smaller. But if you repeat that process over and over, eventually you will reach, as someone noted, an asymptote. You'd have to do the extraction a couple times too. Other questions? Yeah. So you don't have to include the interpreter as bits, and the argument is that the interpreter is something that everybody in the world has agreed upon. If you wanted to, you could include it as well, but you have to call it a day somewhere. And then the idea is the interpreter is not going to have any shenanigans. Though there have been examples where someone's written a compiler that does sneaky stuff. There's a pretty famous Turing Award talk where someone explained that they had hidden a backdoor inside of GCC. It's a pretty good story. Yeah. It is not standard practice to Huffman code a file multiple times because typically an algorithm that uses Huffman coding is actually embedded in a larger algorithm that will make sure to squeeze everything out the first pass. And if you zip a zip file twice, your file will be larger, I promise. It squeezes as hard as you can squeeze. Yes. Yes. You know, that's funny you should mention that. I suspect that is perhaps exactly how that joke from Silicon Valley came to be, is that instead of going top down versus bottom up, you go middle out. I remember thinking about that when I saw the episode, because I think it was around the time I was doing this lecture. All right, so anyway, next time we'll do middle out compression. No. Next time we will talk about some really deep, cool stuff that has to do with this model. Okay, so if you wanted to do something tonight, it's stare at this slide until it makes sense.